The WESTalks has been brought to you by IC Impacts and UBC Future Waters Cluster. The IC Impacts is the Canada-India Research Center of Excellence, and they're focused on carrying out international collaboration and interdisciplinary research, particularly in the water sector. And UBC Future Waters is a pan-UBC water research cluster focusing on interdisciplinary water research as well. Before we go on with the introductions, I just wanted to mention about the WEST conference that is happening in June 2021. The dates are on the screen. And if you're not registered yet, please make sure you register. We're going to put the link in the chat. And we already have some amazing speakers lined up, though I can't reveal the names just yet, but you're going to hear about that soon on the website. The WESTalks Organizing Committee has been at it since last spring, and it comprises of myself, Abhishek. There's Fuhar, Carl, and Leili from UBC, from Dr. Mohseni's lab, and there's Jaskaran from University of Guelph, who is a postdoctoral fellow there, and Feria, who's been updating the website and the videos on YouTube and everything else. This was showed last week as well. This is the places we are getting our participation from and the people tuning in, which is quite cool. We never expected it to be this global, but it's super exciting to see so many people attending our talks. And I guess one good outcome of the pandemic is we can all connect together from across the world. So this week, we have Dr. Megan Mauter from Stanford University, and she's going to be giving a talk on the title Water Sector Electrification, System Level Benefits and Process Level Challenges. Before I introduce the speaker, if you haven't already seen the previous talks on the IC Impacts YouTube channel, you can tune in there. Dr. Ateo, who's also already on the call today, has 320 views on his talk, so that's quite cool, I think. But if you missed out any of the previous talks, please make sure you tune into the YouTube channel. And I'm super excited to introduce today's speaker, because if you're someone like me from the membrane field, you've probably come across this name a lot of times. Professor Megan Mauter holds a bachelor's degree in civil environmental engineering and history from Rice University, and also obtained a master's of environmental engineering from there. She then went on to do a PhD in chemical and environmental engineering from Yale University with Professor Shinadem Osuji and Menachem Elimelech, who was also one of the speakers earlier in WESTalks. She completed her postdoctoral training in the Belfer Center for Science and International Affairs and the Mosawar Rahmani Center for Business and Government at the Harvard Kennedy School of Government, where she was an Energy Technology Innovation Policy Fellow. At Stanford University, Professor Mauter is appointed as an Associate Professor of Civil and Environmental Engineering and as a Center Fellow by courtesy in the Woods Institute for the Environment. She directs the Water and Energy Efficiency for the Environment Lab with the mission of providing sustainable water supply in a carbon-constrained world through innovation in water treatment technology, optimization of water management practices, and redesign of water policies. Ongoing research efforts include developing A-prime water desalination technologies, which I believe was published last year in Energy and Environmental Science, addressing the water constraints to deep decarbonization and developing new technologies for high salinity brine treatment, and supporting design and enforcement of California agricultural water policy. So a lot of work going on in one single lab. Finally, Dr. Mauter also serves as the research director for the National Alliance for Water Innovation, a 100 million Department of Energy water desalination hub to address water security issues in the United States. The hub targets early stage research and development of energy efficient, cost competitive technologies for desalinating non-traditional source waters. So I'm going to hand it over to Megan now for her presentation, and we welcome you on behalf of everybody. And just one last thing, please leave your questions in the chat box and Fuhar will get to them at the end of the presentation. Thank you.
Wonderful. Well, Abhishek, thank you so much for the kind introduction, and to the whole organizing committee for the invitation to present today. Can you see my screen? Great. I have one favor to ask. I've given a lot of Zoom talks at this point, and I really prefer giving Zoom talks to people that have their videos turned on. So for those of you in the audience that are fully dressed, not in your pajamas or, are able to turn on your video, I'd really appreciate it. It helps me as a speaker feel a little bit less disconnected in this global pandemic period. So as Abhishek mentioned, I am an associate professor at Stanford in civil and environmental engineering, and I'm also the research director for the National Alliance for Water Innovation. And I want to sort of start off by saying that none of this work would be possible without an absolutely incredible team of students and postdocs in my laboratory. I want to highlight in particular two people, one of whom graduated and is now at Ohio State, Daniel Gingrich. She's an assistant professor in CEE at OSU. And then also Yang Liu, who is wrapping up the fourth year of his PhD and did a lot of the work that I'm going to share today on sort of the system level opportunities for water treatment systems to participate in electricity demand response markets. So I'll highlight their contributions again at the end, but I owe a big thanks to them. I also owe a tremendous amount of gratitude to the NAWI community, the National Alliance for Water Innovation, which is the $100 million DOE water center that I serve as the research director for. And one of the nice things about NAWI is that it's become this incredibly rich intellectual community where we can share ideas and get feedback on one another's ideas. And really, it's been pushing the entire community to do really innovative research. So as I said, I really owe a lot of that, my lab mission to those dialogues and those discussions, and in particular, this first goal of developing A prime, or automated, precise, robust, intensified, modular, and electrified water desalination technologies, grew out of a lot of those discussions with NAWI team members. My lab also is really interested in how water and energy systems interact, and in particular, how water systems can both facilitate deep decarbonization, but also might constrain decarbonization pathways going forward. And finally, we do a great deal of work on the design and enforcement of water energy food policies, both in California around things like the California Sustainable Groundwater Management Act, but also in this interface between water and energy systems, places like the effluent limitation guidelines or the Affordable Clean Energy Rule, where regulations of water quality affect the way that plants run and operate. So I want to start out this talk by actually introducing a little bit about NAWI, because I think it's helpful for the sort of student community to understand the research landscape in this space. And then I'll jump into a little bit more detail on our work in water electrification and opportunities for demand response, but also some of the issues that might pose for water systems. So the National Alliance for Water Innovation's mission is to secure the nation's water supply through energy efficient and cost-effective water desalination and fit-for-purpose reuse. And the reality is that our conventional water treatment systems were really designed to exploit an ample supply of fresh water to basically treat things once through and send it through a distribution system, treat that wastewater and be able to dispose it readily into the environment. And we know today that changing precipitation patterns, increased urbanization and water demand, aging infrastructure systems through which water is distributed, and regulatory limits on discharge are all driving water users to turn to non-traditional source waters. The issue, of course, is that in treating this non-traditional source waters, we both incur more costs, but also expend more energy. And so we're really focused in NAWI in understanding what are the technology innovations necessary to facilitate a circular water economy and exploit non-traditional water sources, including water reuse, especially to augment and secure our water supply. A key aspect of our mission is to try to make these non-traditional water sources more cost and energy competitive with traditional sources. And so we've set this goal of 90% of non-traditional water sources achieving pipe parity through our technology development efforts. But a lot of that success hinges on how we define pipe parity. And I want to offer up one definition that's kind of our working definition within NAWI, which is that a non-traditional water source achieves pipe parity when the marginal energy intensity or cost is less than or equal to the next available source for a specific end user. So there's a lot of nitty gritty in this definition. The specific end user aspect is particularly important. The kind of cost for one consumer requiring one water quality is very different than that of another consumer at a different node in your distribution system or disconnected from a distribution system might be. But it's also very contingent on this idea that pipe parity is defined instantaneously and in a location specific manner. And so in order to get at that, we actually need to think about water treatment cost and energy intensity as only one of several stages in getting water from its source to its user. In addition to this treatment stage, we also have transmission and distribution contributions to the overall cost and energy intensity of water supply. And that's sort of intuitive for those of you who are in the civil environmental engineering department. You know, we talk a lot about infrastructure, but I think it becomes very easy to narrow our focus down to just thinking about energy intensity of treatment or of a unit process in a treatment train when we're doing research in the lab. So a lot of my work is trying to draw those connections between the benefits of innovations in individual unit processes and what that means for system level costs and energy intensity as a whole. So we actually did a lot of work over the past 2 years to try to develop a method to better quantify what the cost and energy intensity of water transmission, treatment, and distribution were as a function of where you were located in the system and the time of day. And I'm going to share with you right now one example, which is how we might quantify the energy intensity of delivering water to different points in a relatively small distribution network with 330 unique consumer nodes. And what you see here is that you'll notice there's 3 different sources. Each of them have quite different energy intensities. There's a seawater source, there's a freshwater source, there's a long distance water transport source. And you notice a couple of key takeaways. The first is that transmission and distribution energy are often much greater than the energy intensity of treatment. The second thing to take away is that your total marginal energy intensity across the distribution system varies quite significantly based on where you are in that distribution system. But on the whole, that distribution of energy intensity is on the same order of magnitude as desalination processes, right? We talk about water desalination as having kind of a thermodynamic limit of somewhere around 1.1 kilowatt hours per cubic meter. You're not actually able to do that quite that efficiently. So, this range of 0.9 to 1.5 kilowatt hours per cubic meter of actually delivering water suggests that, there's actually a tremendous amount of energy embodied in that transmission and distribution. The final thing to think about is, if we're trying to promote water reuse or the circular water economy paradigm, we typically think of about a kilowatt hour per cubic meter as a relatively safe benchmark for potable water reuse. And so it looks like there's a really key opportunity for potable reuse in this type of system to actually reduce the average energy intensity of the system, even if the energy intensity of treatment is higher. So this is kind of a really interesting deep dive into this breakdown of transmission, treatment, and distribution energy. But it doesn't address kind of what are those key challenges that we need to get there, and what does it mean for water treatment innovations as a whole. And in NAUI, I think all this quantification has been really important in reinforcing an initial hypothesis that we had, that really the only viable pathway for substantially reducing the costs of non-traditional water sources is to replace the economies of scale that we've traditionally seen in treatment size. So as you build a larger treatment plant, the costs and the energy intensity of that treatment tend to diminish. But we want to replace these economies of scale in treatment with economies of scale in manufacturing. So how do you make small scale distributed systems less costly, both to build and operate, so that your overall distribution system costs, these transport costs, diminish, and your total costs shift downward significantly. So I'm not going to go into a whole lot more detail about NAUI's mission, but I do want to say that we identified these 6 challenge areas that are critical for realizing cost-effective small-scale systems. And I'm happy to chat with anyone offline about our research in these particular areas, or point you to our really rich video library on nauihub.org as an opportunity to learn more about each of these areas. But I think I also want to point out that this transition to small scale distributed systems is actually one that's been forged over the past 30 years by the energy industry. So when we talk about the need for supply diversification or decentralization, decarbonization as a driver, like a lot of these features are features that are have been explored in the energy sector for a long time. And new technologies like solar panels and battery storage represent kind of a major shift in the energy industry during that time period. Water is much further behind. We have not realized a lot of these same goals in the water space, but we are rapidly heading there. And so what this talk is really about is some of the system level benefits and process level challenges for implementing 5D water grids, so diversified, decentralized, decarbonized, decoupled, and demand softened, or water efficiency promoting systems, and to think not only about what that means for the water sector, but also what the benefits are of synergistic operation between the water sector and the electricity sector going forward. And in particular, we believe that these 5D attributes will increase the operational flexibility of both power and water supply systems independently, but that the greatest potential in flexibility, efficiency, and resiliency, and the greatest benefits in those areas are really going to come through coordination between power and water systems. So I've already shared with you a lot of the kind of financial and energy benefits of diversification and decentralization in the water sector, and that's really a lot of NAUI's work. But I want to focus the remainder of this talk on decarbonization, decoupling, and demand softening, and the specific research that's going on in my lab to enable those features. So let's start with decarbonization. Existing water and wastewater treatment technologies are chemically and fuel intensive, which means that they're also carbon intensive. When we think about water treatment systems, we have energy inputs, specifically electricity inputs, and we also have chemical inputs. These chemicals actually require a lot of electricity, as well as thermal energy or fossil fuel inputs to manufacture. And so one of the students that I mentioned earlier, Daniel Gingrich, who's now at Ohio State, did one of his thesis papers that's published in ES&T on quantifying what are the human health, environmental, and climate damages associated with water treatment processes. So he did this for every drinking water treatment plant in the United States and developed a comprehensive inventory. He also published a second paper that included quantification of the impacts of wastewater treatment. And in wastewater treatment, you're also using thermal energy to facilitate digestion of the organic load. And you have a number of additional direct emissions from the wastewater treatment plant, including VOCs, methane, et cetera. So the results of both of those studies are published in these 2 papers. But I think what I want to highlight today is primarily the carbon implications of this, or the CO2 emissions coming off of both of these systems. And when we add those up, we find that both, or combined, drinking water and wastewater treatment in the United States leads to about $750 million in climate damages annually. And what was really interesting about this is, my primary interest is in water treatment here, is that in water treatment, such a large fraction of those embedded carbon emissions are originating from chemical manufacturing rather than direct electricity usage. That's very different than what we see in the wastewater sector, where most of it is consumed in aeration of those wastewater tanks. So, on the whole, the balance is heavily skewed towards electricity consumption. But in drinking water, we see a real opportunity for thinking about how to reduce the carbon intensity of chemical manufacturing, and what this means for decarbonization of the water sector alongside decarbonization of our electricity grid. And actually, when we take a step back and think about that balance of chemical, embedded energy and carbon in chemical manufacturing versus indirect unit process energy consumption, it kind of makes sense that it's mostly chemical, embodied in chemical consumption, because almost all of our conventional unit processes in drinking water treatment are chemically based, coagulation, disinfection, et cetera. So there's this means that even though the carbon intensity of the grid is expected to decrease quite significantly over the next 30 years, the carbon emissions from our drinking water treatment systems aren't actually going to change that much. And that has two kind of key implications. The first is that we can either try to focus on decarbonizing chemical synthesis, but that is really difficult. And it is probably going to be more beneficial to try to electrify our unit processes and displace those chemicals than it is going to be to try to decarbonize the chemical industry. The other thing I'll say is that chemical manufacturing includes direct emissions of non-CO2 pollutants that also have significant health and equity impacts. As environmental engineers, aiming at a more sustainable future, accounting for these non-CO2 emissions and their impacts on human health, and in particular, the distribution of those impacts is really important. So we had a couple of questions that we wanted to answer in a paper that's sat on my desk for too many years at this point, but I've promised my former student I will publish in the next couple of months. But we took a stab at a couple of different questions. The first was, what processes should we prioritize in efforts to reduce embedded CO2 in drinking water? What are electricity-driven alternatives that might displace these chemically intensive processes? How clean does our grid need to be for these alternative processes to have a lower carbon intensity? And what are the barriers to adopting and implementing these alternatives? And then finally, if we were to electrify our water treatment processes, what would the climate benefits actually be? So what we found when we dug a little bit more deeply into these set of chemically intensive processes is that the bulk of them, I should say the 95% of them, were attributed to just 3 unit processes: coagulation, activated carbon, and water softening. So we focused on those 3, and today I'm going to only exclusively focus on coagulation. So in order to answer some of these questions, we built a model that evaluated the climate benefits of drinking water treatment electrification. Our approach consists of 2 submodels: a technical model that's basically a process model, and a carbon model. And the technical model calculates the electricity and chemicals consumed in both a conventional and an electrified alternative. And then the carbon emissions submodel calculates the quantity of CO2 emitted per cubic meter of water treated based on that electricity and chemical consumption. And because these are, somewhat different unit processes, we set equivalency standards at the water quality level instead of at the unit process level. So, we needed to ensure, for instance, 90% removal of organic chemicals in order to meet that equivalency standard. So as I mentioned, I'm going to focus primarily on the removal of suspended solids and the displacement of chemical coagulation processes with electrocoagulation processes as an electrified alternative. So the CO2 emissions of any unit process are a really complex function of process design parameters, water quality, and the carbon intensity of the grid. So what I've done here is to plot the CO2 equivalency curves, or basically the break-even point where chemical and electrocoagulation have equivalent carbon emissions for 3 different TDS concentrations, so high TDS in green, medium and low TDS here, as well as a function of electrode spacing and current density, and the carbon intensity of the grid. So this is for the 2020 grid, and this is for the 2050 grid. I know it's a lot to unpack, but basically if the design parameters or the electrode spacing and the current density are underneath that curve, then electrocoagulation is less carbon intensive than chemical coagulation, and vice versa. You'll note that the base case reactor design, so the reactor design in this lower left-hand corner, only reduces carbon emissions under high TDS waters, but optimistic reactor designs with lower electrode spacings are really preferred in all cases. The second thing I want to show here is that we can actually directly present the CO2 emissions for the base case reactor design and the optimistic reactor design as a function of the grid carbon intensity. So we have this, we're basically plotting the carbon intensity of the grid versus the CO2 emissions, and we can look at what that sort of break-even point is for these different salinities. I've shown you this for chemical coagulation, but we've also done this for those 2 other unit processes. And so I've represented that here again, where your grid carbon intensity is on this x-axis and your break-even electricity consumption for that unit process is on the y-axis. So we can use this type of process to set targets for process designs. So, again, if the electrified process consumes less energy than that curve, then it offers net carbon benefits. And one of the important things to note here is that in addition to setting design targets for individual unit processes, we can start to set design targets for entire treatment trains or intensified processes that combine several unit processes into a single step. So for instance, if we were to use membrane-based separations to soften, remove particulate matter, and remove dissolved organics at the same time, as long as that membrane-based process was below this curve, we would realize an overall net benefit. So looking both at the unit process, but also with the treatment train and the intensified process, I think is a really powerful paradigm to figure out where innovation opportunities sit. But I'll also say that we need to ask ourselves if this is really a comprehensive equivalency, right? So I've just shown you all these break-even curves, but maybe there's instances in which electrified processes might actually offer ancillary services to the grid. So benefits to the power grid that aren't realized in this sort of strict carbon calculation. And that leads me to the second part of my talk, where I really want to share some of our work on the benefits of synergistic operation between power systems and water systems. Again, these 5D attributes really increase the operational flexibility of both systems, and coordination between them is, I think, enabled by the kind of high spatial temporal resolution distribution system modeling that I just shared with you earlier. So Let's talk a little bit about decoupling, and really I'm going to focus on demand response services. Uh, Many of you are in the water space rather than in the power grid space, so I'll give you a moment to define demand response, and if you know a lot about it, I apologize for being pedantic. So basically, demand response allows electricity consumers to supply electricity back to the grid by curtailing their demand during peak periods, or shifting their demand to these off-peak periods. So what we see is that instead of consuming electricity during this sort of peak demand time where prices are high and load to the grid is high, we would move our demand to these lower demand periods. And there's been some recent regulation that's allowed independent system operators and regional transmission operators to invite DR participation from anyone that has greater than a 1 megawatt capacity for energy service provision, or for providing these demand response services. And they can do that through the wholesale electricity market. So there's a couple of sort of attributes that go into this bidding process. The first is you have some moment at which you sort of initiate demand response participation. You're sort of notified that you would be asked to curtail your load some period in the future. That period in the future is demarcated by a notification period. So you have some time to prepare for load curtailment. You then actually need to shed your load, and that's defined as TS. And then you have a recovery period. And in the case of a water treatment system, you'd want to recover your tank levels to their business as usual values, and ultimately return to a business as usual pumping schedule after this sort of period of full recovery. And so we have these sort of variables that I hope you can keep in the back of your mind throughout the rest of this talk, of notification, shed, and recovery. And typically the notification and shed would be specified in the DR bid, but the recovery period and the length of that recovery period is really a function of the risk tolerance of the water utility that would want to participate in this demand response market. So why should water utilities think about participating in demand response? Well, the first reason is that they are actually really large electricity consumers. Public water supply systems consume about 40 terawatt hours per year in electricity. They also have a great deal of flexibility, time flexibility in electricity consumption because they have so much water storage, particularly in the drinking water distribution system. It enables flexible pumping schedules, and they already do a lot of flexible pumping in order to reduce their electricity prices and use electricity when it's cheaper in the wholesale market. The third attribute that makes these particularly advantageous is that pumping can stop instantaneously. So you can just turn off your pump, and that means that you can shed load very quickly. So there's been a lot of work on DR participation in transmission systems. And in fact, one of the largest DR providers to the California grid is actually the state water supply system, and they provide a tremendous amount of DR capacity. There's been much less work on understanding what the potential is for water treatment to provide DR services. So we published a paper in Applied Energy last year that looked at the 15 most common electricity intensive unit processes, quantified their energy intensity or their electricity intensity, and then multiply this electricity intensity by the volume of water that each of the plants around the United States treat. Of course, this volume is a function of both season and climate, which in turn influences your total daily electricity load from water treatment in the United States. And of course, DR is not going to be uniform then across the country, and it's also not going to be uniform across seasons. So what I've plotted here is just exactly how non-uniform that is. This is a plot of the aggregated daily flow and average electricity load. Load is on this side and flow is on this side in blue, of drinking water treatment plants across the United States. And the error bars in this load refer to our uncertainty in the electricity consumption of installed unit processes. So, we just don't know exactly how efficient each plant is, and there's wide variability in the efficiency of an individual unit process. The less efficient is, the more DR capacity you have, the more efficient it is, of course, the less you may have. So, I think there, in addition to kind of looking at the snapshot of how much energy or electricity is consumed, this also helps us understand and value the flexibility of that load. And so, as we previously discussed, the flexibility is going to be a strong function of the capacity of the plant to rebound by exceeding normal treatment levels during the recovery period. And so, one way to think about this is the difference between your July water consumption or your peak water consumption and your February water consumption. Obviously, your plant is designed for July flow. So in January, February, your plant could easily recover from that curtailed treatment. In practice, however, this R value, or this recovery, is going to be much larger because plants are commonly designed for future water demand. They're also designed to be able to withstand treatment train maintenance and other process upsets. So what we did in this study is we adopted a very conservative definition of R max as the ratio of a drinking water treatment plant's maximum treatment capacity to its peak day water demand. And the data set we were using for the SIDWIS actually reports the design capacity and then and its peak day water demand. So we were able to do that at an individual plant level. What I've done here then is look at the total DR capacity for drinking water treatment plants in the United States as a function of month, and that's here on this x-axis, the duration of load shedding, or how long you're going to shed load for, and then the ratio of the treatment capacity to its peak day water demand, and that's these three different scenarios with R max. I'm not going to go into these plots so much, but I'll just highlight one example or application here on the right-hand side, whereas kind of July 2018, the ratio of DR capacity from a drinking water treatment plant to the monthly average electricity load is represented by this bar on the right-hand side. So again, TS is the duration of the load shedding period. So your ability to actually meaningfully curtail load is a function of how long you're being asked to curtail load for, and a function of this R max value for an individual plant. So this helps to give us a broad overall assessment of, is this a meaningful contribution? And I'd say that, yes, in certain periods, especially for short load shedding periods and plants that have lots of difference in the treatment capacity and design capacity between summer and winter months, that we can make a meaningful dent or a meaningful contribution to energy services provision in many states, particularly in the West. The other thing that's kind of interesting to note is that this is probably going to grow significantly over time. So we've seen an incredible uptick in the adoption of membrane-based separation processes that are very electricity intensive relative to other separation processes. And so further process electrification, adoption of RO, adoption of electrocoagulation would also increase demand response capacity. There's a lot, and I say that kind of optimistically, but I also want to say that there's an amazing amount of research that needs to be done in just how sheddable this load is and what it means for how we actually operate these unit processes. So, this is a Canadian water treatment network talk, so I want to give a shout out to Amy Bilton, who's at University of Toronto, who's done a little bit of work on the sheddability of load for membrane-based processes and what that means for the longevity of those membranes, for instance, and how you might want to manage those membrane systems differently if you thought you were going to be ramping and trimming your operation on a regular basis. So that was kind of a highlight on treatment, but as I mentioned, most of your energy intensity is actually embodied in transmission and distribution. A lot of work has been done on transmission, so I'm going to focus here a little bit more on the distribution side. And we also published a paper in January 2020, about a year ago, on a risk-aware decision support tool for demand response and water distribution systems. We did this for a skeleton distribution system in the UK, serving approximately 20,000 people. And as I mentioned, these utilities are already shedding their load or curtailing their pumping when electricity prices, which are plotted this blue line and referenced on the right-hand side axis, when those electricity prices peak, these distribution systems are shutting down their pumps. So this is the business as usual sort of load or pumping profile. And what we asked in this paper was, if we use that optimized pumping schedule as the baseline, we can still ask what additional load shifting capacity pump scheduling might provide if an emergency demand response call was issued. And typically higher rates are paid for these emergency demand response calls. So it's a real opportunity for profitability, but it also helps to do things like stabilize the grid. When your Texas grid shutdowns last month during a cold snap are a really good example of where, when you have grid instability, you can kind of lead to widespread electricity outages. So we investigated the optimal pumping activity for several different cases with different notification periods, shed lengths, and recovery periods. And I'm not going to go into all of these different cases, but I'm presenting one here where our recovery period is an 8 hours. So it's these 3 cases are plotted in these 3 lines. And what this lower graph shows is the optimal load curtailment fraction under different compensation prices. And remember that electricity markets are what are setting these DER prices. So water treatment providers have an opportunity to decide whether or not they want to participate at a given price, and they could use these plots to help them make that decision. I'll also point out here that our shed fraction and the ability to shed load and reduce pumping is going to be a sort of a direct function of how much or how long you are shedding load for. So you can shed more of your load if you're only shedding it for an hour, but if you're shedding it for 3 hours, you really can't shed all that much of your load and make sure that this distribution system is providing its primary function of delivering water to consumers. So what we see, the high level takeaway is that whenever the prices are up in this quadrant, so above these curves, it's beneficial for utilities to participate in this emergency DR market. And there's a limit on how much they can shed, and that's represented by this asymptotic line. So ideally, they would bid all the way up to this maximum shed fraction and recoup as much of that additional revenue stream as possible. The question is is this actually a significant amount of revenue? And in this case study, the average wholesale electricity price was about $20 per megawatt hour. So plants have the potential to collect pretty significant revenues through DR participation. You see that they're bidding somewhere around, anywhere above that 20% limit is realizing profit for these distribution systems. And if the DR markets go up into this range, which they often do, you have the opportunity to really harvest a great deal of additional revenue. And in this example, it was about 4% of their electricity costs. So, we're not talking free electricity, but we are, that's a significant potential revenue stream for these plants. Okay, I want to wrap up by just talking a tiny bit about some of our work in demand softening. And demand softening could include a lot of different things. It could include water efficiency improvements, or it could include distributed water reuse platforms. So I showed you this slide earlier where we were focused on developing a flow backtracking method for instantaneously and spatially resolved analysis of the marginal energy intensity of supplying an individual consumer. And while this is really useful for doing that, this method is also useful for several other applications. The first is that it's incredibly useful for understanding where to invest water conservation dollars. So where do you deploy water efficiency interventions? Where do you promote water recycling, and how do you cite, where in your distribution system do you cite water reuse facilities? It's also a very useful tool for enabling a regulator or utility to establish efficient time and location specific water prices. And it could also be used as a tool for realizing carbon reduction goals without costly infrastructure upgrades. If you don't convert this to dollars, but instead you convert this to CO2 emissions, you actually find that there's a tremendous amount of variability in your CO2 intensity of distribution as a function of time of day. So let me just provide a couple of examples in designing water conservation campaigns. If you were to target the lowest MEI consumers, or the consumers that consume the least electricity in supplying those consumers with water, versus the highest MEI consumers in the single source network, you would deliver exactly the same water to different consumers, but you would, the same total water to those consumers, but you'd save 16% of your energy. Another example application is to figure out where to deploy decentralized supply and distributed reuse systems. So, where do you deploy a small scale water recycling unit or potable water reuse unit? There's a couple steps in that process. You'd want to rank and select the highest MEI consumers. You'd then want to understand how the marginal energy intensity sort of compares relative to the consumers' sort of energy intensity or MEI within their grid. And then you can determine the maximum fraction that is satisfied by that decentralized supply for each of those consumers, and rebuild this distribution curve, or this sort of, I should say, this CDF of all of these different consumers in the presence of these water recycling units. So what this shows is basically that anywhere where it's white it represents an energy savings relative to the status quo. And we can use this to say, it's actually significantly better to cite a recycling unit in these locations than it would be in some other locations. And that's a paper actually that has now been submitted as of this week. Finally, we can use this to inform real-time water prices for industrial users, which we don't really do today, but there's a tremendous opportunity to incentivize things like irrigation in the middle of the night instead of irrigation in the middle of the day, where you might have both higher electricity prices, but also some issues with ensuring stability of the grid and minimizing the costs of water distributions for those utilities. Okay, so all of that to say that I think there's a tremendous opportunity for a 5D revolution in the water treatment space and distribution space, but the real benefits are going to come through synergistic operations of these two rapidly evolving infrastructure systems. And I think there's a lot of additional work to be done here, and hopefully as the next generation of environmental engineers, you were excited enough about this talk to be inspired and work on some of these challenges. So I want to again highlight Daniel Gingrich, who's now an assistant professor at Ohio State, and Yang Liu, who's a fifth-year PhD student, fourth-year PhD student, for a lot of their contributions to this effort. And with that, I will take questions.